What we want to look at now is figure out, well, how does charge vary as a function of time? When we close the switch, the capacitor doesn't charge instantaneously. It takes time. So can we derive an expression for this? So yes, we can. And the way that we're going to do it is we're going to look at this loop here, and we're going to use Kirchhoff's loop rule that says that the sum of all the potential differences around a closed loop is equal to 0. So let's start right here, and let's look at the potential differences as we go across. First, we're going from the negative to the positive terminal of the battery. That's a positive E plus E. And then we're going across the resistor here. We're going in the same direction as the current, right? We know the current is going clockwise because it flows from positive to negative terminal. So when we go with the current, that's a drop, minus IR. Now what I'm going to do now is instead of using a capital I for current, I'm going to use a lowercase I. And this is because this is going to be the instantaneous current, so the current at any time. We know that the current does change, right? Because we said at the beginning we have a lot of current, and then when the capacitor is fully charged, we have no current. So since the current is varying, it doesn't have a fixed value, I'm going to use a lowercase I for the instantaneous current, so the current at one specific time. So at whatever time that we're looking at, what is the voltage drop across the capacitor? To find this, we can once again use the equation for capacitance, C equals Q over delta V. So that means that V is going to be equal to Q over C. And instead of using a big Q, I'm again going to use a small q because charge is varying as a function of time. So this will be the instantaneous charge. This is over C. So this is the sum of all the potential differences. It's going to equal to 0. And now we want to go ahead and solve for Q, but we can't just get Q by itself because we know that I also depends on Q. For remember, the current is the derivative of the charge with respect to time. So we have to get all the terms that have I and Q on one side and all the other terms on the other side. Let's go ahead and bring let's see, what we can do first is we can do E minus Q over C equals IR. And let's go ahead and have a common denominator here, which is C. So let me just use a different color here. It's going to be a little bit math intensive here. We're going to have that common denominator, and we're also going to divide by R. So what we're going to get here is CE minus Q, and it's all over C, except we're also going to divide by R. So it's going to be over RC. That way we get the I by itself. And we know that I is dq over dt, so we can go ahead and make that substitution, dq over dt. And now we can get all the terms that have q on one side and actually the terms that have everything else on the other side. So on the left-hand side, we're going to get dt and 1 over rc. And then on the right-hand side here, we're going to get 1 over CE minus Q dq. Now to get Q by itself, we're going to have to integrate both sides. And the limits of integration are going to be from 0 to Q over here and from 0 to T over here. We know that at time 0, there's no charge on the capacitor, and at time T, there is a charge Q on the capacitor. Let's go ahead and integrate. Over here, we just get T when we integrate the dt, so we get T over RC. And then on the right-hand side here, we're going to integrate by substitution. We can do U is equal to CE minus Q. So that means that du equals negative dq. So we're going to have the integral of negative, I'll write it here, it's going to be the integral of negative 1 over u dq. And so that's going to be a log, so we're going to get negative log of u, and the limits they used to be from 0 to Q, but when we plug that into U here, it's going to be from CE to CE minus Q. All right, so it got a little bit crowded there. So that's going to be, and we can go ahead and move the negative to the other side here. So it's going to be, well, actually, let's just leave it there for now. So negative log of CE, let's see here, CE minus Q minus the log of CE, but when you subtract logs, you can just divide here. So now let's move over here and simplify this. We're going to go ahead and move the negative to the other side. So we're going to get negative T over RC equals log of CE minus Q over CE. We can go ahead and take the exponent of both sides to get rid of the logarithm. So e to the negative T RC over RC equals CE minus Q over CE. We're almost done. Now we can go ahead and multiply both sides by CE to get rid of this. And then we can add Q and subtract all of this to the other side to get Q by itself. So it's going to be CE minus all of this here, CE e to the negative T over RC. And we're basically there now. So that means that the charge as a function of time is equal to CE, we can factor it out here, times 1 minus e to the negative T over RC. Now, what is CE? We know that a charge times a voltage is, we know that a voltage times we know that a capacitance times an EMF, a capacitance times a voltage is a charge. And we know that when the voltage is E, that means that we have our maximum charge on here. So we can rewrite this if we want to, using the fact that CE is the maximum charge, as we saw earlier. So we have our expression for the charge as a function of time. What does this look like? It looks like this kind of exponential curve. And this is charge as a function of time. At the beginning, we have 0 charge. And then the charge builds up really quickly, but the more charge that you have, the charging slows down, right? Because it's harder and harder to charge it up as more charge accumulates, because these charges that accumulate, they make it harder to bring more charges, right? Because they repel them. So for now, we don't have to worry about this tau. We're going to learn about it in a couple of videos. It's called a time constant. For now, we just have to know the shape of all of these graphs. And so when we have the 1 minus e, this kind of expression is always going to look like this. Let's go ahead and look at now the current as a function of time. What does that look like? We just saw in the previous slide that the charge was given by this expression. Now we know that the current is the derivative of the charge with respect to time. So all we have to do is take the derivative with respect to time of this function. So what we're going to get here, first of all, CE times 1, the derivative of that is 0, so we can just ignore this first term, but now we have CE times negative e to negative T over RC. So the constant negative CE, we keep to the front. Now we're taking the derivative of this with respect to time. So it's going to be negative 1 over RC times e to the negative T over RC. Right, since we already brought the negative here to the front. Because we know the derivative of the exponential is still the exponential. And now we can simplify. We have the two negatives cancel out, and we have the C cancels out. I wanted to use a different color here. So we end up with the negatives canceling out. We end up with E over R e to negative T over RC. This is the current as a function of time. Once again, we can make a substitution for this if we remember the E over R, that is the maximum current in the circuit. Remember from a few slides ago that was the maximum current when we only had the resistance of the resistor that was inhibiting the flow of charges. So there we have it, our expression for the current as a function of time. What does this look like? It's going to look like this graph over here. So whenever you have an e to the minus t over rc term, the graph goes down. We start with maximum current in the circuit, and then it decays until the capacitor is fully charged up, and then we have no current. This is the current as a function of time, and once again, don't worry about the tau, just know that this is what happens as time goes by. Finally, let's take a look at the voltage as a function of time. First, let's look at the voltage on the resistor. Well, we know that the current in the circuit is given by this expression over here. So this is the current through the resistor at any time. So to find the voltage across the resistor at any time, we know that voltage is current times resistance. So we just have to multiply this by R to get this expression over here. So this is the voltage on the resistor as a function of time. Don't have a nice printed out graph for it, but whenever we have the e to the negative RC term, it looks like this. We have maximum voltage, and then it's going to decay because as the capacitor charges up, we have no more current in the circuit, then we have no more voltage across the resistor. And we can also obtain an equation for the capacitor voltage as a function of time. To do that, we use the equation that we found for the charge on the capacitor as a function of time, which was this equation. And we know that C equals Q per voltage. I always have to write it down to solve for it, so delta V is Q per C. So we know that if we have charge as a function of time, but we want voltage as a function of time, we just have to divide this expression by C. And that is how we obtain this expression. And what this is going to look like whenever we have the 1 minus E term is going to look like this. As the voltage on the resistor decreases, the voltage on the capacitor increases. There's no voltage at first on the capacitor, but then as it gets charged up, you end up having maximum voltage on the capacitor.